Hey, what's up, guys? Yeah, so today, let's keep doing some NP complete reduction, and what I'm gonna do here. Okay, okay. So what I'm gonna to do here today is that I want to connect this NP complete question in a graph, and provide three proof, sorry, two proof. Okay, if you haven't seen my previous NP reduction video, that I will provide a list. I will provide a link below so you guys can check. Okay, so our goal in this video is to prove that vertex cover and also independent set and also the k-clique. Okay, so these three are NP complete. Okay, so I first will connect three of them, and I will provide two proof. Okay, so one proof is that using my previous video, that if you prove that we can prove that three set can be polynomial reduction to three color, and the three coloring that I can prove that this is polynomial time reduction to this independent set. Okay, and another is much more simpler, is that you start from three sets and directly go to k-clique. Okay, so I will provide these two proof. Okay, so let's start. Before I start, let me just spend some time talking about the definition. Okay, so the settings that somebody give you a graph G, which is the vertex and edge, and let's talk about what vertex cover mean. Okay, so vertex cover means that and also given an integer, a positive integer k, should be greater or equal to 1. The vertex cover means that let me just define vertex cover. So vertex cover is a subset of the edge, also it's a subset of the graph, such that okay, so you pick a subset of the vertices, and for yeah, so it's a subset of vertices. Sorry, I should say this. Okay, such that for every edge, let's say belongs to E, that every edge has 2 points, right? Has 2 vertices. So E incident on B prime. So which means that each edges must at least touch one vertices in the B prime. Okay, maybe this is hard to understand. Maybe let me just draw something. I suppose this is our graph, and let's say I choose this, and I choose this. Okay, so now for each edges will touch one red point. So these three are the vertex cover. Okay, so the problem is that the definition is that the vertex cover, right? Such that for this is the vertex cover and a given k. So the question is a decision question. Ask whether there's a v prime which is a vertex cover, such that this v prime is less or equal to k. Okay, so obviously that if you choose all the points, then if you choose all the vertices, then it's vertex cover, right? So the difficult problem is that if you put k to be smaller, then it becomes difficult. Okay. Okay, so let me just remind you that in the NP complete, the problem that this k is unlimited, so you cannot choose. When I say vertex cover is NP complete, I say that for every k from 1 to the number of vertices you can arbitrarily change this arbitrarily. Okay, the reason is that for fixed k. Okay, suppose you just fix on k. Okay, you fix k, then you can just choose, right? You can just, let's say, unchoose k, right? So you can just unchoose k vertices and check whether and check in polynomial time, right? So you just need n of k, unchoose k and the poly n to check that this is, so for each fixed k, this is definitely polynomial time, right? But if you choose k can be arbitrary from 1 to n, then it may be exponential. Okay, the second question is the independent set. Okay, so independent set. So independent set is this, right? So the same thing, but you take the sub vertices, and the v prime is independent. So when I say v prime is an independent set, means that for every so I should say there's no edges, so there's no edges between v prime. Okay, so basically for each v prime, that for each 2 point of v prime, there's no edge vertices. Okay, so given k, you should ask whether there is a independent set greater or equal to k, right? Because if you don't take any point, if you take 1 point or 2 points, and then obviously you can easily change, right? But if k increasing, then probably this is difficult. Okay, and the final is called k-clique. Okay, so for example, this is 3-clique, this is 4-clique. I just I did some stupid thing. Let me just try to recover it. Okay, so this is the 4-clique. Okay, so basically this k-clique means that you want to ask whether there is a k band notation, but this means the complete graph for k vertices. For example, this is complete graph for super vertices, complete graph for 4 vertices, and also complete graph for 5 vertices. Basically you create 5 vertices, and each 2 vertices are unconnected. By the way, this is called a complete graph. Okay, so you want to ask where there's a complete graph, which is a subgraph. Subgraph means that you take the vertices and also the edge, subset of G. Okay. Okay, so this is k-clique. Okay, so this is a very simple definition. I hope you understand this. And also in this 3 question, that k can be arbitrarily small or arbitrarily large. So we'll make this problem become np-complete. Okay, so let's quickly prove the. Okay, so I want to prove the reduction. So I want to tell you the how to do what is the relation between it. Okay, so reduction of the vertex cover, and also independent set, and also k-clique. Okay, so this proof is almost trivial. So let me just quickly say it. Okay, so I mean, okay, so hope you guys understand definition. Okay, so first let's do very simple case. Let's prove that so fact 1. Okay, so fact 1 is that let's say if you the vertex cover. So notice let's say that G is a VE, and then that V prime is a vertex cover of size K. So V prime is a K, and the V prime is a vertex cover of G. And what you can get, right? So this is simple, right? You take the every points outside of V prime. Okay, so you just take. You can you can define another V tilde defined to be V delete V prime. Okay, so simple exercise is to check that V tilde is an independent set. Then I should say then V tilde is an independent set of size n minus k. Okay, this is trivial, right? Because there are n minus k number. Okay, proof. Okay, so proof is just logic, right? So let me just write down. So okay, so this is not actually not then. This is if only. Okay, so V prime is a vertex cover, and if I take the complement, then V tilde will be independent set of size n minus k if and only if. Oh, so proof is very simple. Let's take the independent set. Okay, so I mean that's just V prime is a vertex cover. Okay, so that means that for every edges, right? For every edges, that at least one of its ends touch or belongs to V. Okay, this is the same as what? This is the same as you just do the logic, right? So this tells me that if I take V tilde, then which means that the V tilde divided by V minus V prime, which means that for every edges, now V prime is another, right? So this can use when you do the negation, you change at least one to be no, right? So no ends touch it. Oh no, ends belongs to V, right? So for every edges, no both and at least one, right? So this is no. Okay, so no both ends belongs to B tilde, right? So just negation, right? For every now, the first one is that for every edges that at least one of is n is in B, right? But I do the negation, so it means what? It means that no so this is at least one. So there'll be two of them, right? Or one of them, right? But this should be so I should say this is both ends should not belongs to in V. Okay. So this means that for every edges, you should not find the 2 points on these edges. Both belongs to this V tilde. Okay. So this is by definition, this is an independent set. Okay, probably it's not easy to see, but let's do this example. Right? If I take a complement, then I take this screen, right? And there's no edges between them. Okay, very simple because now for each edges, you at least touch one of it, right? So if you take a complement, then there should be no edges between it. Okay. So this just tell you that for every edges, at least one of these, that means that for every edges, both ends do not belong to V. Okay, this just tell you that no edges between V tilde, right? Okay, so you can check this. By yourself. Probably it's not difficult, but proof is just what I say. You just write everything down and try to understand the logic. Okay. Okay, so hopefully it's okay. So let's consider another one, which is the independent set and the k-clique. Okay, so this is actually the polynomial reduction, right? So suppose someone can solve the independent set, then you can solve vertex cover. You can solve vertex cover, then you can solve independent set. Okay, what is the relationship between the k-clique and the independent set? Okay, so let's say we start from VE, and the very simple theorem is the following, right? So the k-clique means that the k-complete graph, right? So if you take out this k-complete graph, or you empty all the edge, right? So this means that somebody gives you this, which is k-clique, right? If you remove all the edges, this become independent set. Okay, so this gives you a feeling that you can construct G prime, which is independent, which is a so-called reverse graph, which is the same vertices but edges. That's called E tilde. So E tilde means that all the edges. So sorry. So E tilde is okay. So let me just quickly define this. It's called a so-called reverse graph. Simply speaking, a reverse graph is just remove all the edges and you add all the edges which is not be connected. Okay, so for example, this is original graph, and then you do this is G, and you do the reverse, which give you this. Okay, so this edge is already connected, right? So I just remove, and these do not connect, so it becomes this. Okay, so I don't write the definition, but you know what I mean. Okay, so this is called the reverse graph. Okay, so obviously that if you have a k-clique, right? If you have a k-clique in your subgraph, right? Let's say this is original graph, and then you have the k-clique, which this is a k-complete graph. Okay, then you can try to see something, right? You can if you okay, so this is k-complete graph, right? So if you remove this, you empty all this you remove all, reverse this graph, right? Then there will be no points connected, right? So this tells you that if G has size k independent set, independent means that no vertex is connected, right? Only if G prime has a k-clique. Okay, the trivial, right? Because k-clique contains everything, and then you empty all the edges, so it becomes k-independent set. Okay, so this is a simple polynomial reduction that contains every of it. Okay, so we do. So now we prove that these three guys are actually polynomial reduction to each other. So now we can prove. We can try to prove using this proof to prove that they're np-complete, right? Because previously they already showed that I can do a 3 set to 3 coloring. So actually this is the set. Okay, but directly show 3 sets contact to k-clique is much easy. So this is the easier one to prove that 3 of them is to prove that 3 of them is np-complete. This start from 3 set to k-clique. This is a trivial one, and the much difficult one will be I will also talk about is you start from a 3 coloring and go to independent set. So this is difficult. Not so difficult. But I think the proof of this kind of NP reduction is interesting. That you can try to think by yourself and find that actually the previous people, some of them are still very smart. Okay. So first, I proved that the 3 sets actually can be, let's say, k set, or basically k set means okay. Let's okay. So let's go. Okay, so 3 set is actually can be solved by k-clique. Okay, so this problem is simple. Okay, so this is proof is very simple. Okay, so let me just quickly illustrate the idea. So let's do something. Let's say I solve this x. Let's say somebody give you this. Actually, I don't know whether this is satisfied or not. I just plug in something. Okay, the funny thing is that for each, so you want to make a graph, right? So the idea is that you first draw, let's say x1, x2, x3, right? You draw, let's say x1 bar, x2, and x4, and let's say you draw x1 bar and x4 bar and x2, and you draw x1, x bar, x3 bar as a node. Okay, and you use the 3 coloring approach. So x1 and x1 bar are contradictory to each other, so they should not be they should not be connected, right? So you can connect other points. So idea is that x1 do not touch the x1 bar, and then you can connect in everything. For example, x1 can connect itself. I mean this is fine, right? And you connected this. Okay, and x2 bar and also x2 do not can connect everything except for x2 bar. Probably this looks stupid, right? But let me just shit. Sorry about this. X2 bar should be here. Okay, so let me just draw a little bit. Okay. Okay, then you draw the S3. Okay, so I mean it's difficult, but you can draw yourself. Okay. Okay, it become complicated. Okay. So the idea is that now you can ask the question. You can ask where there is a fork link. Okay, so if so, this is 4 of them, right? You can ask where is fork link. Okay, suppose I find fork link. Okay, let's say I find fork link. Maybe that I find something which is not easy to see. Let's say I find maybe x2 to x3, and then x3 to x1, and then maybe x1 to let's say x4, and then hopefully maybe I find this. Maybe I find this fork link. Okay, I find it. Okay, so this is fork link, right? Then I can set each to be true, right? So I set s2 to be true, s3 to be true, and x2 to be true, and x1 to be true. Okay, so if x1 is true, this is true. When x2 is true, this is true. When x2 is true, this is true. And when x1 is true, this is true, right? Which is true. Okay, so this is trivial, right? So now you see the idea. So idea is that you ask if there is a fork link, that means that you can find a assignment for each clauses such that there's no contradiction. right? Because if there's a contradiction that x1 do not contain x1 bar, right? So if you can find any clique, there's no contradiction that you can find clique such that you make every clauses which is satisfiable for each clauses, right? Because if you make this assignment to be true, then this guy will be true. Okay, so you can simultaneously make everything to be true without contradiction. Okay, so the idea is that if you have m clauses, then you can construct. Then you just ask whether there's a m clique. Okay, so now let's prove the results. And if you cannot find it, then you obviously this is not satisfiable. Okay, the reason is this: if it is satisfiable, then you should find it, right? So I mean, if this is satisfiable, then you can connect and find clique. If you cannot find clique, then obviously it's not satisfiable. Okay, so simple proof. Okay, so this is a proof, and then you can see that this is a polynomial reduction. Okay, then the reason is almost trivial, right? Because you have m clauses, right? So you get m clauses, and then let's say, and for each 3, right? So you at most get 3 m variables, and the number of edges. So number of edges is bounded by OM squared. Okay, and then if your number of clauses is poly n, then you at most get poly n edges. Okay, so which is a polynomial reduction. Okay, so this is a trivial proof, right? So when we prove this, we get everything. Okay, so now we are ready to go to the final one, which is a proof that will give the reason that the 3 coloring is actually related to the independent set. Okay, so this is not obviously, but so let me just introduce something which is new. Okay, so so the problem is that what's the relation between the coloring or between coloring and independent set. Okay, so the idea is that let's define chi of g to be the chromatic number. Okay, chromatic number is the minimum number or minimum number of colors that you can color the graph. Okay, so simple example will be if your G is bipartite, and only if chi of G is 2. And the 3 coloring just ask is the same as you ask whether chi of G is greater or equal to 3. Okay, then let me define alpha of G to be the largest independent set. So largest size of independent set. Okay, so what's the relation between them? So notice that if G has a chi of G coloring, so if G is a K coloring or K colorable, means that I can use K color to separate G, right? And each vertices do not have the same color. So this tells you that G has a K independent set, modulo independent set. Okay, so let's label this set to Xi. So this tells you that your G as a vertices V can be written as a union of Xi where I belongs to K. So I from 1 to K. So 0, 1 to up to K. Okay. So which tells you that and there are modulo inclusive, right? So each vertex can only belongs to one independent set. So this tells you that the number of vertices is the sum of the size of Xi where I from 1 to K. Okay, and the largest one is the alpha of G, right? By definition. So this is the number, right? Alpha of G. Okay, and this is K, right? So now I choose K to be chromatic. So which give you this. Okay, so this is the identity, which is inequality, which is very non-trivial. That the number of the chromatic number probably not non-trivial. As proof is already given. A number of the chromatic number times the number of largest independent set is the number of vertices. Okay, but what the hell is going on, right? I mean, about this problem, just for fun. Okay. Okay, so still one, which is not probably obviously, but you can think a little bit. So if a G is a three-colorable, if G can be G can be written as the largest. There is a largest independent set of G. So let's say X is the largest independent of G, and the union the rest. Okay, so G. Okay, so this is as a vertices, such that G mod X, you forget about all the, or you forget about all the edge which connected to X, is a bipartite. Okay, actually, this gives you the algorithm that you can solve. You can use a three-colorable solve independent set, or using an independent set to give you some information of three-colorable. Okay, so let me just quickly give you the proof, and the proof is not it's simple, right? So let's say G is a bipart. G can be written as the largest independent set, and the rest is bipartite, right? The rest is bipartite means that I can use two colors to get a rest, right? So I can. So that means let me just draw this. This is G, and then I get X. Let's say this is X, okay? And I say the rest that I can use, and there's no two there for every point in X. There's no connection, right? So there's no contradiction here, and then the rest is bipartite, right? So that means I can use two colors to I can use a red, and then let's say blue, let's say a green. Okay, so to color this edge, and then, so there's no contradiction for this one, right? No contradiction here, and then no contradiction here, and no contradiction, right? So because these points and these points, even though there is a connection, there are different colors. Okay, so now this G is a three-color. Okay, so this direction is almost trivial by definition. Okay, so how about this? G is three-colorable, and one can solve the independent set. This is maybe you need to think a little bit. So let's prove the another directions. Okay, so let's say G is three-colorable. Okay, so that means I can find the three color, let's say, so I can separate the vertex of V into three parts. Let's say this is a blue part, okay, and the red part, and the green part. Okay, so B is an independent set. Okay, so one of it must be, I can choose one. I choose one of them, which is a size of greater than equal to 3. Right? I can always find at least one of them is greater or equal to this. Okay, so let's say B is the largest one. Okay, so there's no edge. So suppose if B is the largest independent set, then I get a problem. I solve the problem, right? If B is not the largest independent set, that means I can increase B. Okay, so I can find maybe here for some maybe these points, these vertices do not have incidence on B, right? Do not have incidence, so I can change this to B. But once I change this to B, all the edges connect to red and blue do not have a contradiction. Also G to blue, right? They are different color. There will be no contradiction. Okay, then I can put this B into in it. Then I start to increase my dependent set until I cannot go to. Okay, so then B becomes the largest independent set, and then R and G belongs to the bipartite graph. Okay, because these two colorable, so by definition, it must be bipartite. Okay, so this is the proof. Okay, so now I think we proved this one, right? Because the three coloring can go to independent set. Okay, so for example, if one can solve the largest independent set, one can solve the largest dependent set, then one can easily do this, right? Because for this one, that somebody give a graph, right? So, and let's say one can solve in largest independent set, so he can use a point. Let's say he give you some polynomial time, where I guess there's no polynomial time, right? But if somebody can solve this independent set easily, then you can check that the rest of the graph is bipartite, and this is just polynomial time. Okay, so which means that three colorable can be boiled down to independent set. Okay, so in this video that we proved three sets is k-clique, and we also proved that vertex cover, independence, and clique, they are both related to each other. So we proved that all of them are NP complete. Okay, by this video. Okay, so see you guys next videos.